Hi everyone. Today I'm gonna go over the LeetCode problem, find minimum in rotated sorted array. So first, let's read the question. Suppose an array of length n sorted in ascending order is rotated between 1 and n times. So for example, the array nums equals to 0, 1, 2, 4, 5, 6, 7 might become 4, 5, 6, 7, 0, 1, 2 if it was rotated 4 times, or 0, 1, 2, 4, 5, 6, 7 if it was rotated 7 times. So when you rotate the array, you rotate to the you shift to the right. So like the last element becomes the first element, and so on and so forth. And so given the sorted rotated array nums of unique elements, return the minimum element of this array. And you must write an algorithm that runs in O of log n time. So this O of log n time specifies that we need to use binary search. And so let's look at an example. Here, right, in example 1, the input array nums is 3, 4, 5, 1, 2, and we return 1 because it's the smallest element. And here it says the original array was 1, 2, 3, 4, 5, and it was rotated 3 times to get 3, 4, 5, 1, 2. So first I want to go over an example and like point out some patterns. So let's see that the original array is 1, 2, 3, 4, 5. So this is original rotated array. If you rotate it once, so like R is like the number of rotations. If it's rotated once, we get 5, 1, 2, 3, 4. Right, because like you rotate it this way. Actually, sorry, that's a you rotate it like this, right? Like you rotate to the right. So if you rotate 2 times, you get this. If you do it 3 times, you get this. Four times, you get this. And 5 times, you get this. So I want to point out some like patterns or properties. The first one is if you rotate the array n times, where n is the number of elements, you get back the original array. Like for example, here I can see this original array is like 1, 2, 3, 4, 5. Once you rotate it 5 times, you get it back. And because we know that, because the question stated that the original array is sorted in ascending order, here, suppose an array of length n sorted in ascending order. Because we know that the array, like the original array is already in ascending order, we know that then the first element must be the smallest element. And how can you like do a check, right? Because you don't get a number of rotations given to you. The only time when the first element is less than the last element is when the number of rotations is equal to the number of elements. So here, right, like if you look at 1 rotation, 5 is bigger than 4. 2 rotations, 4 is bigger than 3. 3 rotations, 3 is bigger than 2. 4 rotations, 2 is bigger than 1. 5 rotations, 1 is less than 5. So we can do a simple check, and let me just write like some Python pseudocode here. I guess the array is called nums, right? So I'll use n to abbreviate nums. No. Oh, sorry. Oops. And then there should be an n. And the reason why we're doing this less than or equal to is in case there's only 1 element in nums, right? So this is like this is an edge case that we can use at the beginning of the function before we do any of the binary search, it's a quick simple check. It just checks, like it just compares the first element with the last element. And if it's less than or equal to, like if the first element is less than or equal to the last element, we know that the first element must be the smallest one. So we just return it. We don't even have to do binary search. So we have this case done already. I can cross this out. And another like byproduct, like another result of this is that we now know that the first element can no longer be the smallest element. So in like I assume like in all other cases, we know that the first element can no longer be the smallest element. And this helps with property number 2, which is that the only time in one of these, like the only time when an element is smaller than its predecessor is if that element is the smallest element, and it can only happen once. So for example, right, if you look here, we can from here on out we can like ignore the first element of each array, because we know that it can't be the smallest element. If it is, it will have been picked up here. So we're going to start from the second element. 1 is less than 5. 2 is bigger than 1. 3 is bigger than 2. 4 is bigger than 3. In this case, right, 5 is bigger than 4. 1 is less than 5. 2 is bigger than 1. 3 is bigger than 2. And the property remains the same for these two arrays as well. So the only time when an element is smaller than its predecessor is if that if that element is the smallest element. So we have our, I guess, our check condition. So before I do that, let me just write some variables. So we're gonna, because we're doing binary search, we're gonna need a couple of pointers, left, right. And again, n is just the nums array. N is just like an abbreviation for nums array. And we're gonna need a mid. And again, because we're doing binary search, we need a loop. So I'm going to do a while loop. So if this element is strictly less than its predecessor, we just return it. And we don't have to worry about any like out of bounds issue, because the only time when an element does not have a predecessor is if that element is the first element. And we've already established that if like the first element of an array is the smallest, it will be returned here. So we don't have to worry. There's no chance of like an out of bounds like index out of bounds error happening here. So this is our like our return like check or something. So now have you know, like when are we going to like use the left half, we use the right half? So let me do this 1 second. Let me I guess zoom out and move over a bit. So I'm sorry, 1 second. So this uses left half. So yeah, so this Aleph statement means that we're gonna use the left half. And so let me explain, right? If the middle, if like the middle number, so the middle element is less than the if the middle element is less than the first element, like then what we know is that all well, first thing we know is we know this middle element is not the smallest element, right? Because if it was the smallest element, it would have been picked up here. So we know that this middle element is not the smallest element. And we know that there's no way that it can there's no way that it can what do you call it? Sorry, there's no way that sorry. We know that this element it's not the smallest element. And we know that all elements to the right of this element is bigger than it. So because of that, we know that the right half of the array is useless. Sorry, let me re-explain. So let's use an example. So let's say that we have this, right? This is when we rotate this array once. So this will be our middle element. I'll just say this is our like our m mid, and we see that it's smaller than the first element. Well, we know that all the elements to the right of this element cannot be smaller than it. Like for example, we can have something like this, right? Like this, something like this wouldn't be possible because earlier I said, right, the only time when an element is smaller than its predecessor is if that element is the smallest element. Well, actually, sorry, that's a bad example. Let me do something like, let me change this to this. Let me change this to something like this. So the only time that an element is can be smaller than its predecessor is if the element is like the smallest element, and that can only happen once, right? But in this case, you see that in this case it happens twice. 1 is less than 5 and 2 is less than 3. This means that the original array wasn't sorted in ascending order. So because of this, because we know that first this element is not the smallest element, and we also know that no element after it can be like all elements after this has to be bigger than it, right? So we know that we can just write them off. We don't care. We just focus on this half. And similarly, if I do this, so this uses the right half of the array. Oh, sorry. This should be greater than. Sorry, my bad. Sorry. This should be greater than or equal to. Yeah. So first thing is the reason why we need this equal to is for the edge case of when there's 2 elements in the array. And so let me explain this, right? So let's use another example. So let's say use this. I'm gonna do it here. So this 5 is our m mid. So we see that this 5 is bigger than this 3, right? So because of this, we know that all elements between the first element and this middle element, the value has to be between theirs. Again, like if you have something like this, that means that the original array wasn't sorted in ascending order, which is a violation of the condition, right? So all elements between the first element and this middle element must also have the values between the 2 elements, right? And so we already know that the first element is not the smallest element. And so basically all elements after the first element and up to including this middle element is bigger than this. So we can write off this half and just focus on these 2. So let me re-explain everything. So let me close this. So the first property that we saw was that the only time when the first property we saw was that when you rotate the array n times, where n is the number of elements in the array, you get the original array back. And because we know that the original array was sorted in ascending order, we know that the first element must be the smallest element. And we also know that the only time when the first element is less than the last element, or less than or equal to the last element, is when you have the original array back, right? And so because of that, we know that if the first element is less than the last element, then we know that the first element must be the smallest element. The second property we saw was that the only time, the only time when an element is smaller than its predecessor is if that element is the smallest element. And we saw, right, like 1 is less than 5, 2 is bigger than 1, 3 is bigger than 2, 4 is bigger than 3. So we can use this property for our check. That's what we did here, right? If this element is smaller than its predecessor, we just return the element because it's the smallest. But there's more to that. So assuming that like the middle element that we assemble upon wasn't the smallest element, if the middle element is less than the first element, then we know that the right half of the array, starting from that middle element all the way to the end, it's not needed. The smallest element cannot be in the right half of the array. And the reason for that is because if the smallest element is inside that right half, then there will be 2 times when there will be 2 instances of when an element is smaller than its predecessor, but there can only be 1 because the array was sorted in ascending order, like the original array. So it's not possible for the smallest element to be in the right half. And similarly, if the middle element is not the smallest element and is bigger or equal to the first element, we know that the smallest element cannot be the left half of the array. And the reason for that is because the reason for that is because the original array was sorted in ascending order, if the smallest element was in the left half, like it will break that condition, right? And so all the elements in the left half, they must be in ascending order. And we already know that the first element isn't the smallest element, so we can just use the right half of the array. So now let me call this up. So L is going to be the left pointer, R is going to be the right pointer, and oops. So this is what I was talking about earlier, right? If the first element is smaller or equal to the last element, then we know because of this property, and the fact that the only time this happens is if we have the array sorted back to its original form, that the first element must be the smallest element. So here is a mid. So here, right, this part, this is what I was talking about earlier, where the only time that an element is smaller than its predecessor is if that element is the smallest element, and this can only happen once. Like for example here, right, you see that the only time when an element is smaller than its predecessor, assuming there is one, is here, right? And in this case, because the n is equal to 7 and we rotate it n times, this would be caught in this check. So now, oops. So this part, right? This part is when we don't need to, it's when we like remove or discard the right half of the array. And the reason for that is because, so we know that this num_smid is less than, we know that this num_smid is less than the starting element, And we also know that this num Smith cannot, like, it's not the smallest element. If it was, then it would be called like here, right? So because of that, that and the fact that there's only like the only one time when the element is smaller than its predecessor is if like that element is the smallest element. We know that all elements from num Smith to the end is in like ascending order, so the smallest element cannot be there. And on the flip side, we can disregard the left half of the way if the middle element is greater or equal to the starting element, because then the left half, that part of the way must be in ascending order, so the smallest element cannot be there. And we also know that the first element is not the smallest element because it would have returned otherwise. So we can discard the left half. So let's run this. Okay, and let's submit this. And yeah, and like I mentioned before and stated in the question, this is the time complexity of this is O of log n. Thanks for watching.